Here we're going to solve a so-called relative velocity problem. These are typically problems involving an airplane and figuring out the flight plan. This also works for a boat crossing a river or just moving across a current. If we're talking about an airplane, generally speaking, we'll be given three pieces of information. We will know how fast the plane can fly. In this case, the airspeed is 150 miles per hour. That's generally speaking given because that's how fast the air has to move over the wing in order for the air to generate enough lift to keep the plane in the air. So once we know what type of plane we're flying, generally speaking, we'll know how fast we're going to be going. It's always a good idea to know where you're going. So generally speaking, we will know our destination. We should know both how far away it is and in what direction it is. I have to be a little careful because those are two very different pieces of information. The last thing we can generally take for granted is we'll know the wind, because if worst comes to worst, we can contact the National Weather Service and ask them what the wind is. They will tell us how fast it is blowing and what direction it's blowing. Generally speaking, we'll often be given the direction it's blowing out of, which means not the direction it's blowing towards. If it's blowing out of the southwest, for an example, here we can draw our little compass headings. Whoops, that's not south, that's east. North, south, east, and west. Blowing out of the southwest, that's the southwest down here. So it's blowing out of the southwest, which means it's towards the northeast. So when we draw our vector, we'll be going out of the southwest and towards the northeast. That's a common mistake, is when you see out of the southwest, many people will draw the vector that way. That's backwards. It's blowing in the other direction. Now, usually what we want to find is what direction do we aim our airplane? Now, you might guess, well, if I want to fly north, wouldn't I take my airplane and direct it north? And the answer is no, because you have to compensate for the wind. And therein lies the problem. The heading is basically the direction of the velocity of the plane relative to the air. So what direction do I point my airplane in? The other thing I want to know is, when am I going to get there? What's the arrival time? Well, the arrival time comes from the velocity of the plane relative to the ground and this distance right here. How far am I going? Now, the equation we're going to be using, which we will write out right here, is the relative velocity equation. It is always the velocity, that's a vector, of the plane relative to the ground is equal to the velocity of the plane relative to the air, that's a vector, plus the velocity of the air relative to the ground. And this right here is the wind. This right here is the airspeed. And this right here is the ground speed. Notice this forms a triangle. I am adding two vectors together. This vector could be the velocity of the plane relative to the air. And this vector right here is the wind, the velocity of the air relative to the ground. And their sum is the velocity of the plane relative to the ground. Basically, this equation and this triangle are equal. And generally speaking, the easiest way to solve these kinds of problems is to draw the triangle rather than trying to do a bunch of algebra. So the problem usually is taking what we are given and drawing this triangle, figuring out what angles we know, which sides of the triangle we know, and then using geometry and trigonometry, laws of sines and cosines, to solve for the unknowns. Now, what we want is the direction for the velocity of the plane relative to the air, which we aren't given. The other thing we want to know is the arrival time, t. Well, that is always equal to, effectively, a distance divided by a speed. Except we've got to be careful because this is how fast the plane is flying. And this is how far it's going. However, this is how far it's going relative to the ground. Therefore, this must be also relative to the ground. Or this must be equal to the velocity of the plane relative to the ground. And here's another very common mistake. The distance I was given here, which was 300 miles, and the speed I was given, let's go back, the problem told me I'm going 150 miles per hour. But that is relative to the air, so I don't want to take this and divide it by 150 miles per hour and say it takes me 2 hours. This would be wrong because this is relative to the air and this is relative to the ground. To use the speed and the distance, they must be in the same frames of reference. So I have to calculate this number before I can do this calculation. Another common mistake. So let's take and draw our triangle. And here we have our various pieces set up. Here is the equation we're going to be using right here to draw our triangle. And the way to draw this triangle is actually a little strange. The best way to do it is to first draw the resultant, the sum, the velocity of the plane relative to the ground. That is, in this case, a vector pointed due north. So I'll put it right here, and it's pointed north. I don't know how long that vector is, because the 300 miles is a distance, and this is a velocity. So that is not a vector, which is 300 miles long. Another common mistake. Notice this is a velocity triangle. There are no distances involved. They are only speeds. So this is my resultant. Namely, I want to add these two vectors up so that I end up with a sum that's pointing north. I don't know how long that sum is. But this is the long side of my triangle. To that, I want to add, to get that, I want to add basically the airspeed. So I'm going to start by putting that vector at the beginning of my resultant. Namely, I'm going to add these two vectors up, but in the opposite order. And that's another thing that makes drawing the triangle easier. Because this vector, I know the length, plus I know the direction. So this vector right here, in our problem, go back to the problem, should be basically 40 units long and should be out of the southwest and towards the northeast. And that's what this is, out of the southwest and towards the northeast. And it is 40 units long. So that vector, I know exactly how to draw. That's just going to get in my way, so I'm going to erase that. And that's just going to get in my way, so I'm going to erase that. Now, what I want to do is I want to take and add this vector right here. I know the length of this vector. This vector right here is 150 units long. But I don't know what direction I want to fly in. And the direction I want to fly in is basically given by along the fuselage of the plane, which is parallel to the velocity of the plane relative to the air. And I don't know what direction I want to fly in. Again, let's get rid of this. It's going to be in my way. This vector right here can be oriented in any direction to get me to where I want to go. So I can turn this in any direction, but its length is fixed. So what I want to do is take this vector right here, put it along the end of the airspeed, and just turn it until I end up with the direction I want to be. And on this particular program, that's a bit of a pain because it pivots around the center rather than around the end. But that's pretty good. So that means I want my plane to fly in this direction. And conveniently enough, this plane is going in the right direction. So my plane would actually fly along this path relative to the ground 300 miles. And notice it's not aimed due north. If it were aimed due north, the wind right here would blow it off course. But if I'm aimed a little bit into the wind, like this one is, the wind will blow me on course, and my plane will fly like this, due north, aimed a little bit to the west. Now, notice right here, I have my triangle. Let's just highlight it. This right here is my triangle. And my problem now is, which angles in that triangle do I know? And which sides do I know? And what don't I know? And then I use basically geometry and trigonometry to solve the problem. So, we'll go on another slide. All I have now are the sides of the triangle. This right here is the wind, and I know it has a length of 40 miles per hour, so I'll just write that as 40. And I know the bottom angle right here is 45, and my destination is north, so that this right here is a right angle, which means, I'm just going to delete this because I don't want that in my way. This angle up here must be 45 degrees. So I know one of the angles in the triangle. This side right here is the airspeed, and I know that is 150 units long. I don't know that direction, so I don't know any of the angles for this vector right here. All I know is that it's got to be 150 units long. This side right here is the ground speed, and I don't know how long that is. So I have one angle, and I have two sides of my triangle. I'm going to get rid of this because, again, that'll just get in my way. So we have our triangle. Now we're just going to label some unknowns. I'm going to call that angle right there x at the top. I'm going to call this angle right here y. And this, since I know it's going to be the velocity of the plane relative to the ground, I'll call it that. So one side I don't know, two angles I don't know. Now, what we can do is we can use the law of sines and the law of cosines. Generally speaking, if you can, always use the law of sines. The law of sines tells me that the sine of an angle divided by the opposite side is always equal for all the ratios. So here I have one angle that I know, and I know the length of the opposite side. So that tells me that for this case, the sine of 45 degrees divided by 150 must equal, well, here I have a side, and here's the opposite angle. So this must equal the sine of x divided by 40. And I can solve that for x. And if you rearrange this and solve, x turns out to be 10.87 degrees. I'm going to keep some extra sig figs just so I don't have any round off errors in my calculation. So now I know x. Now I get to use some geometry because this is a triangle, and the sum of all the angles in a triangle is 180 degrees. So that must equal basically 45 degrees plus x plus y. X I now know, so I can solve that for y. Y is going to turn out to be a big angle, and I kind of expect that. That's what it looks like in the triangle. And that turns out to be 124.13 degrees. I now know y. Now I can again use the law of sines because y is the angle opposite my only unknown left, the velocity of the plane relative to the ground. So I can set that equal to the same ratio right here, the sine of 45 divided by 150 equals the sine of y, which I now know, divided by my unknown velocity of the plane relative to the ground. We can rearrange that and solve that for the velocity of the plane relative to the ground. And that ends up equaling 175.6. Now I know everything about the triangle. The problem is the 175.6 is one of the things I do want to know, because that will be miles per hour. But my angles are none of the right angles. The angles I know are the angles inside the triangle. Let's take a look at the angle I actually do want to know. And to do that, let's draw essentially right here. This is pointed east. And let's draw another line pointed north. The angle I want is the plane is pointed in this direction. This is the direction the plane goes, the red vector. This right here is the angle I want. Let's call that H for H being the heading. That's the angle I want. I don't have that angle right now. I know this angle right here is 45 degrees. I know the angle between the blue and the red vector is about 124 degrees. This angle right here, the angle of the blue vector beneath the east-west axis, is also going to be 45 degrees, because this is a right angle. Green is pointed north. So this is a 45, 45, 90 right triangle. So this angle is 45 degrees. This angle right here I can get because it will be 124 minus 45 degrees. That'll be this angle right here. The heading is from north, so this angle right here is 90 degrees. So the heading will equal 90 degrees minus this angle right here, 124 minus 45, and that'll be the heading. And that turns out to be about 11 degrees. So I'm going to point my airplane 11 degrees, and notice this is on the western side of north. So that'll be west of north. And that's the heading I have. Recall where we started. We had our airplane flying a little bit to the west. And this is our airplane right here, flying a little bit to the west. And we now know that that little bit to the west is our 11 degrees. We don't want to fly our airplane due north, because if we did, the wind would basically blow us off course. The wind wants to blow us in this direction. So if we aim due north, the wind's going to blow us over here. So therefore, we actually aim ourselves a little bit into the wind, and that a little bit into the wind is our 11 degrees. So this angle from north is our 11 degrees. Heading is 11 degrees, oops, that's not 10 degrees, 11 degrees. 11 degrees west of north. The velocity of the plane relative to the ground is about 175.6 miles per hour. The time it's going to take is relative to the ground, we are moving 300 miles, and we are flying at the rate of 175.6 miles per hour. So that is the division we want to do. We do not want to use the 150. Notice what happened here is the wind actually sped us up a little bit, because the wind was a little bit coming from behind us. So rather than 2 hours, we're traveling a little bit faster. We're going to get there in 1.71 hours. In general, the way we want to always solve these kind of problems is we first draw that triangle. And to me, the easiest way to draw the triangle, so we always have the right triangle. Typical problem is students will solve the triangle correctly, but they'll have the wrong triangle. It'll be pointed in the wrong direction. To me, the way to do this is to first draw the vector that describes the destination. Making sure there I just know the direction it's going in, I don't know its length. Just make that vector really long. Then, since we know the wind completely, we draw that vector starting at the beginning of the destination vector. Then we draw a vector for the plane's airspeed, because we know that, starting at the end of the wind and keeping going until we reach the destination vector. We now have a triangle. We solve the triangle using basically geometry and trigonometry. So this is another general problem we have. Our destination is over in this direction somewhere. So we'll draw that destination vector. Indeterminate length, simply pointing in the right direction. So let's say we know this angle right here is given. Then we have our wind. Our wind is blowing in some arbitrary direction, so we take the wind vector and we move it over here so that it starts at the beginning of the destination vector, blowing off in this direction. Now we have two sides of our triangle. Notice we know this angle right here. This is given, this would be the destination, and this is given, this is the wind. Because this is 180 degrees right here, notice we'll know one of the angles inside the triangle. Now we need to add the third side, and that comes from the airspeed right here. Airspeed, we will know this length, but we won't know what direction to point it in until we put it in the triangle. So the length of this vector is given. However, we're going to have to take this and turn it around, figure out what direction do we want to go in. And we want to go something like this. Not quite. Let's move it up a little bit. Unfortunately, again, this program pivots from the center, not from the end. So something like this. So we want to aim our plane in that direction. We now have our triangle. Our triangle is this mess right here. We'll know this side. This is the velocity of the plane relative to the air. That is known. This side is known. The velocity of the air relative to the ground. And as I just argued, we will know that angle. So now we have a well-defined problem in basically geometry. We know a side right here, we know a side right here, and we know an angle right there. Then we use the law of sines to get the remaining unknown angles, and then we use the law of sines again to get the remaining side. And that is, in general, how you would solve one of these problems.